We now wish to examine when a matrix with repeated roots diagonalizable or repeated eigenvalues is it diagonalizable. The terms now we want to introduce is called algebraic and geometric multiplicity. Algebraic multiplicity means how many times the multiplicity of the eigenvalues of one of the particular eigenvalue. So if we have, for example, the eigenvalue is 1, 1, let's say 2, 4, then the algebraic multiplicity of the eigenvalue is 2, in this case for eigenvalue 1. Here, algebraic multiplicity for the eigenvalue 2 is 1. Here, again, 1. What about geometric multiplicity? Well, remember that associated with each eigenvectors, associated with each eigenvalue is an eigenvector. So if the algebraic multiplicity is 1, then there is only one eigenvector for the eigenvalue. But in this case, when the eigenvalue is repeated, then the dimension of the eigenspace here can be 1 or 2. So the geometric multiplicity is talking about how many vectors in the basis for this eigenvalue, or we should say the dimension of the eigenspace corresponding to this eigenvalue, if this is the matrix of eigenvalue in the diagonal. Alright, let's see. We need to introduce the term eigenspace. Alright, the eigenspace is the space spanned by the eigenvector of corresponding to this particular eigenvalue. Okay, now given A, let's assume lambda is an eigenvalue of A, and we can find the eigenvectors of A. The eigenvectors of A is simply A x equals to lambda x, and therefore we will get A minus lambda I x equals to 0. The non-zero vectors of x are the eigenvectors, and simply it is the null space of this solution. So we're now repeating ourselves. The null space of this matrix is a space because if this is a non-zero vector, any linear combinations or any scaled versions of this vector is a solution. What is interesting is that it can be formed by a few factors. So this space is not dimension only one. It can be more than one dimension. That's the interesting thing. All right. Now, so when we are examining the eigenspace, we must fix lambda. We must be studying the eigenspace only for one particular eigenvalue, and all the eigenvectors for such that the eigenvalue is lambda actually will form the eigenspace. Okay, let's see. In this simple example of a 2 by 2 matrix, it was given to us that -1 is an eigenvalue of A. Once we are given an eigenvalue, we can compute the eigenvector, and this is the eigenvector. It is only a single eigenvector, and therefore we say that the eigenspace of A for the eigenvalue -1 is spanned by these eigenvectors. That means any linear combination of -1, 1 multiplied by any scalar still is an eigenvector. And we have seen that before. We say the eigenvector is along this direction, and it can be scaled by any constant. And if we want to flip the direction, we multiply alpha as a negative value, and we'll flip the direction of the eigenvector. Okay, for sanity check, you can use EIG again. You plug in the values of A into EIG, generating P and D, And we see again that we get two eigenvectors, and one eigenvector is, one eigenvalue is 2, the other eigenvalue is -1. This corresponding to the eigenvector of 2 and -1 respectively. Now, because these eigenvalues are distinct, therefore each of these eigenvalue have only algebraic multiplicity of 1. What about geometric multiplicity? Well, remember, algebraic multiplicity is the number of repeated roots is related to the number of repeated roots, which is the root, the power of the root. So geometric multiplicity is the dimension of the eigenspace for that particular eigenvalue. So simply, the geometric multiplicity is the dimension of the eigenspace. So what does dimension means? Dimension is the number, it is a cardinality, or it is basically counting the number of vectors in the basis for that vector space. So we're talking about this vector space, the eigenspace of matrix A for this particular value, how many vectors need to form the basis. That's the dimension. Okay. In our previous example, since A has an eigenvalue of -1, and we found only one eigenvector associated with -1, therefore the geometric multiplicity of EA minus 1 is equals to 1. Okay, the dimension of this space is, geometric space is only 1. In other words, determining geometric multiplicity is nothing but counting the number of vectors in the null space of this matrix. Now let's have another example. This example A is 1, 2, 0, 1. We plug in A here. Again, we plug in A into EIG. We get P, the first eigenvector, the second eigenvector, and we have 1, 1 as the eigenvalue. So 1 is repeated 2 times. So the algebraic multiplicity of lambda equals to 1 is 2, because the eigenvalue is repeated twice. So algebraic multiplicity is higher than 1. What about the eigenvectors? Now here gives you a hint. The eigenvector, actually, well, you think that it looks different, but in fact they are pointing to the same direction. The second eigenvector is simply pointing to the opposite direction of the first eigenvector, but they are still pointing to the same direction. So what does that tell us? The second eigenvector is not independent of the first eigenvector, which is a scaled negative version of the first eigenvector. And therefore, in this particular case, this matrix cannot be diagonalized. You can try also by finding P minus 1, and you realize that you cannot find because the determinant is 0. So that again is review. So why did this happen? Well, one thing is that when we have repeated eigenvalues, sometimes we are lucky, we can find a full set of eigenvectors, and sometimes we cannot. Okay, that's the problem. All right.